Second, slow gain. Okay. So we have to review the materials we studied in lesson 3. In lesson 3, you might have remembered when solving either slow Setrov absorber or slow gain, we have to separate the time axis into 2 stages. There is no easy solution for the entire time window. We have to separate into 2 stages. Stage 1 is defined as this. Absolute value of t is close to 0. That means this area, okay, around the pulse peak. Okay. In this area, our conclusion is like this. The gain as a function of time is about g, okay, this is a typo, superscript, g superscript I, the initial gain, which is denoted here, times an exponential decay function, where the exponent is the cumulative pulse energy, U of t, over the saturation energy, U sub g. Okay, it's derived in lesson 3. So roughly like this. Around the pulse peak, the gain saturation curve is a monotonically decreasing curve. Okay, because even passing through the pulse peak, the energy continues to be accumulated. Okay, so the saturation continues. It's not like the fast Setrov absorber. The pulse peak corresponds to the minimal loss. Okay, so this is the signature of slow Setrov absorber or slow gain medium. Then in stage 2, we got a different model. When time is greater than t prime is defined here, the pulse tail, g of t is governed by this relation. Basically, it's an increasing function of time. When time increases, your gain slowly recovers to initial gain, actually trying to recover to the small signal gain. But since this is a pulse trend, it can only recover back to initial gain rather than small signal gain. Okay? And the formula is like this. And we also know the recovering time constant is no longer tau g, depending on material only. It's tau g prime equals tau g over 1 plus w times tau g. So this is about the pump rate. Okay, if you have a stronger pump, your denominator is bigger, then your recovering time constant is shorter. That means it will recover faster. Okay, this is our model. But in solving the passive mode locking, we make some approximations. Okay, for example, in stage 1, okay, we already assume even the total pulse energy is much smaller than the saturation energy. So it means weak gain saturation. Then this is the original stage 1 formula about the gain curve. Okay, if total pulse energy is much smaller than Ug, that means your exponent is a number much smaller than 1. Correct? Because U of t is always less than total pulse energy. So if even total pulse energy is much smaller than Ug, this must be a very small number, much smaller than 1. Then you can use zeroth order Tyler series approximation. It's close to e to the 0, which is constant 1. So you got g of t is close to g super I, the initial gain. Okay. So forget about mathematics. What does this mean? It means in stage 1, the correct response curve is like this. But in our model, it's almost a constant curve. and there is no secrecy. It simply results from the pulse energy is too weak. So this saturation curve is very shallow, too shallow to be identified. So almost like a constant. Okay. But we have stage 2 to deal with, right? In stage 2, we also assumed repetition period is much smaller than the gain recovering time constant, tau g prime, and of course, it's shorter than tau g. This is so-called slow gain recovery assumption we have made in the beginning. So let's re-examine the formula in stage 2. Okay? If this assumption is correct, then very similar, this term is close to 1 because the exponent is close to 0. T minus T prime is always less than repetition period. Okay? So it means 你去看跟 T prime 的时间差，你最多 stage 2会延伸到什么地方？就下一发脉冲来了，对不对？等到下一发脉冲来，你又回到 stage 1。那下一发脉冲什么时候来 ？Roughly speaking, TR, right? Repetition period. After one repetition period, the next pulse comes in. So within the entire stage 2, you can always say T minus T prime is always less than TR. Okay. And in that case, TR is also much less than tau g, so the numerator is much smaller than the denominator. So this is a number very smaller than 1, close to 0. And the e to the 0 is 1, constant 1. Okay, so if you do that, this is 1, you got G0 minus G0 plus G minima. So you got this result. The stage 2, the gain dynamics is close to a constant G minima. But according to the stage 1 formula, we know the minima gain is nothing but initial gain times exponential decay term. And if you use the same approximation before, the factor is close to constant 1 as well. So you also got G of t is close to initial gain, G super I. So no matter is stage 1 or stage 2, you arrive at the same conclusion. Gain dynamics, G of t, is close to a constant gain, G super I. Okay? So this is a very simplified model. You don't have to worry about gain dynamics in this case, because in this case, gain is just a constant. It's regarded as a constant. But be careful, G super I is not equal to G0. It's not equal to small signal gain. Because after all, your Morlock laser is lasing, right? If it's lasing, it has average power, non-zero average power. Then in that case, your gain, even though it's a constant gain, it's smaller than the small signal gain, as we have known in lesson 1, right? It means gain saturation. We discussed in CW laser theory in lesson 1. Okay? Then the next question is, okay, we know we don't have to worry about gain dynamics. G of t is a constant, G super I. The next question is, what is the number, G super I? Okay? So this slide is dedicated to the calculation of G super I. How could we find the answer? Let's check this figure. The first pulse, your gain saturation response. The second pulse, the response repeats. Okay? So interesting thing happens here in stage 2. The idea is this. It takes one repetition period to recover from the minima gain, G minima, which is here, okay, the lowest point, to the initial gain, G super I, which is denoted here. So in terms of formula, it's like this. G in stage 2, T prime plus TR, so that means after one round trip, what is the gain? The gain has to return initial gain, okay? So just use this relation, and using the gain dynamics formula in stage 2, G of T equals G0 minus parenthesis G0 minus G minima times exponential decay term. And also using the relation minima gain equals G super I times decay constant, e to the minus total pulse energy over UG. Okay, so 1, 2, 3, you just need these three relations. So you can have this one, 你把它带进这个关系式，然后这个 function of time 就用它，然后出现 minima gain 就用它，你就会得到这个 relation. Okay? But we need to simplify the relation to arrive at a very easy result. Okay? So what assumptions could we use? This is repetition period is much shorter than the gain recovering time constant, and the total pulse energy is much smaller than the saturation energy. Okay? If you use them, what happens? 1 minus e to the minus tr over tau g, since tr is much smaller than tau g, so you can say this is close to e to the 0, which is 1. But if you do so, 1 minus 1 equals 0. You got nothing. So you cannot use zeroth order Tyler series approximation, but first order Tyler series approximation. So this is not 1, but 1 minus tr over tau g. You need two terms. Okay? And 1 minus 1 can cancel with each other. So only tr over tau g is left. So that's the numerator. For the denominator, you do the similar thing. The first term, you use first order approximation. Second term, also first order approximation. Then 1 minus 1 can cancel with each other. Only the two ratios are preserved, okay, in the denominator. So this is the result. Initial gain is approximated by an adjustment factor times G0, the small signal gain. And of course, the adjustment factor is less than 1 because initial gain is always less than small signal gain. Okay? But you can reorganize, okay? Dividing TR over tau g for numerator and denominator simultaneously. So the numerator becomes 1, denominator the same thing, so this is 1 plus a factor with 4 terms here. Okay? But if you check the definitions, you can see total pulse energy over repetition period. It's simply the average power, right, of your pulse train. 每一发脉冲的能量除以脉冲与脉冲之间的时间间距，一除完不就是这个脉冲链这个 pulse train 的 average power. So the first one is average power. How about the second one? Tau g over UG. There is definition as well. This is the so-called saturation power of the gain medium. Okay? So the 4 terms can be simplified to a ratio of 2 terms. Your average power over the saturation power. Okay? So this is the result. Your constant gain is governed by this simple formula under our assumptions. But this formula is an old friend, right? We have seen that in lesson 1. This is the same formula as in CW lasers. we derived in lesson 1. Okay. So the simple conclusion is, although this is about passive Morlock post-trend, but if you only consider the gain dynamics, it only follows the CW laser formula. The constant gain. The gain is no longer a function of time, but a constant, close to a constant. And that constant can be precisely calculated by the CW laser gain formula. Small signal gain over 1 plus average power divided by the saturation power. So only average power is important. There is no information about the rise or fall of the pulse, right? 这公式完全看不到脉冲的存在，它只在乎平均功率而已。这就回到 CW laser 的情况。Okay, any question? So what have we done? We derived the formulas about loss dynamics and the gain dynamics. Loss dynamics is fast, so it's there. You cannot treat your loss as constant. But gain dynamics is too slow. It's just like a CW laser. It's constant. So we got these two conclusions. Then let's go back to the master equation. Okay, so this is the original complex master equation. Under our assumptions, it can be simplified to a real master equation because we have assumed there is no GVD, this term is 0. There is no CEP shift, so psi is 0. There is no cell phase modulation, so delta is 0. These 3 terms, all of them are purely imaginary terms, are cancelled. Okay? So everything else becomes real. Besides, G of t originally it's about gain dynamics, but according to last page, this is a constant gain only. So G of t is substituted by constant G. The G is governed by the CW laser formula. How about loss? Under our model of fast Setrov absorber, L of t is close to L0 constant loss minus SAM coefficient gamma times your driving laser power, P of t. Okay? So then you can simplify the original master equation into this one. Second order time derivative with a leading constant 1 over omega c squared plus a so-called term, time-dependent term, G sub big T of t times A of t itself equals 0. So this is a very simple differential equation. Okay? But what is G sub big T? It consists of 3 terms. Okay? G, LC, L0, gamma, P of t. So totally it's like this. G minus L plus gamma PT, and L is a new constant, LC plus L0, representing the linear loss. Okay? LC is the cavity loss, maybe due to the mirror, it's a constant. L0 originally comes from L of t, it's a dynamic loss, a nonlinear loss. But even the nonlinear loss, there is constant term. So the contribution can be combined with the contribution of LC. Together, you got the linear loss term, L, which is LC plus L0. And the G sub big T means the net gain. Gain minus total loss, right? L and the gamma PT means the total loss, the cavity loss and the dynamic loss. So gain minus loss means net gain. Okay? So the physical meaning of this term is net gain. 你总共看到的 gain 有多少？它是你看到的 gain 再扣掉你看到的 loss， 剩下如果有正的，就是 net gain； 剩下如果是负的，你就看到 net loss。Okay, so that's the meaning. Any question? I have a question. Is this equation, okay, this one, a linear second-order ordinary differential equation of time-varying coefficient? If it is, then you should be able to quickly write down the solution according to the knowledge you study in the sophomore year, right? 如果是线性二阶常微分方程，只是有10变的系数啊，一定10变嘛，对不对？这是一个 function of time。那你应该很快就可以写出 solution， 但它是不是 ？No。Why？
你后面有2个 t 的 function 乘在一起。
后面是哪里？
就是 g of t 跟 a of t 那2个乘在一起。
OK， 所以 g of t 有什么？有 p of t。What is p of t? Roughly speaking, it's absolute square of a of t. So g of t is not an independent time-varying coefficient. It includes the unknown function a of t itself. So if you have a of t absolute square multiplied with a of t, certainly it's nonlinear. So this is a nonlinear differential equation. It also means all the well-known solutions you have studied before does not apply. Okay? The solution cannot be simple exponential function as you expect from the linear ODE theory. Okay, it's a very different story. So the answer, quick answer is, the solution to that nonlinear equation is like this. Second hyperbolic solution. A0 is the amplitude of the second hyperbolic. Tp is the width of the second hyperbolic. Okay, so A0 and the Tp are two unknown constants, but the shape is fixed second hyperbolic. Okay, but you might ask me, how do you know the solution is a second hyperbolic function? Given the equation is nonlinear, usually nonlinear equation may have very strange solutions, as you have known. How do you know the solution is a simple second hyperbolic function? I don't know. The pioneers are very smart. They just find the solution works. Okay. So I plot this figure to show you the solution shape. Okay, 大概像长这个样子。It's not a Gaussian function. Okay, and the peak power is about A0 square, the square of your amplitude. Okay, total pulse energy means the area of this curve is 2A0 square times Tp. It's about your peak power as well as your pulse width. Okay, and the average power is this number, total pulse energy over repetition period. Okay, so if you know A0 and the Tp, you can quickly write down the corresponding parameters, peak power, pulse energy, average power of this pulse trend by these formulas. Okay, without going through the like integration here. 就是说，严格说来，你必须找出 solution， 再去做积分，你才可以算出这些东西啊。但是这个形状已经固定了，所以你事先做好，一旦 A0 Tp 解出来，这些统统都找到。Okay. So if you think this is the solution, how do you find A0 and the Tp, the two unknowns? Just substitute this solution into the original equation, okay? But if you substitute into this equation, you will see there are only two possible functionals. One is Sech, second hyperbolic function. The other is the cubic of the second hyperbolic functions. Only two possibilities. And that's why you can find the governing equations for A0 and the TP. Okay. So maybe let's take a rest of 10 minutes, and we will move on to the solutions.